Welcome back to ECE 501B. I will see you this week, but next week will be a different story. Monday, there's no class that I'm aware of. It's Veterans Day. Monday, you won't have to come to class or campus for that matter unless somebody's having a lecture for you. It won't be me. I might give you something, but it will be remote. It will be online or through D2L. Also, a week from Wednesday, you won't see me here. I will be somewhere else on Wednesday, so don't show up here expecting to see something happening in class unless you guys want to have your own party. Information about 501B, okay? Just to let you know that we are getting close to the end. We have 2 more homework assignments, and here are the dates of those. The project deliverable is essentially a paragraph, 3 or 4 sentences that tell me what you're wanting to do. That's deliverable number 1, which is due the Wednesday prior to Thanksgiving. That's on the 21st. And the final exam is on a Tuesday. So if you're used to thinking 501B, Advanced Linear Systems Theory, only on Monday and Wednesday, you need to start training your mind to be able to do that on a Tuesday, because the final exam is on a Tuesday and it's from 6 to 8, so it won't be starting at 4. Question? The final exam will be comprehensive, yes. So you can't completely forget. It all sort of builds anyway. What we saw on exam 2 relied on some material that you needed for exam 1, for example. And deliverables 2 and 3 for your project are due the last day of class, which is a Wednesday, and that's the 5th of December. Deliverable number 3 is really a reflective paragraph. What did you learn? What do you think about what you did? And it doesn't have to be very big. The big part of this project is deliverable number 2. Today what I want to do is continue with chapter 7, which is operators on inner product spaces, and we'll start with normal operators, and we'll give an example, a matrix representation example of what it looks like to be normal. What does it look like to be normal as an operator? We will find out, and then we will do or state proposition 20, which says T is normal if and only if the norm of TV is equal to the norm of adjoint TV for all V. Where normal, did we define that last time before the exam? Maybe we did not. So now we're specializing these operators. We've had linear maps, we've had adjoints, we've had operators. Now we're specializing these operators to be self-adjoint, maybe. Today we're talking about an operator being normal. And for an operator to be normal, that means it needs to commute with its adjoint. T dagger should equal T dagger T. That's what we mean by normal. And if we have a normal operator, that actually can be thought of also in terms of norms. It means the norm of that linear map T, or that linear operator applied to any vector V, is the same as the norm of the adjoint of that map applied to the same vector. That seems to kind of feel good with norms, using that second idea or concept behind a normal operator, and that's proposition 720. All of these specializations of operators or maps are designed to give us a way of thinking about nice operators or maps, ones with lots of zeros when we think of their matrix representation. We've talked about upper triangular, we've talked about diagonal. Diagonals are nicer than upper triangular, for example. And how do we get these? Well, we actually get them by looking at more and more specialized maps or operators, and in particular normal operators are becoming more nice than just an operator. We'll look at then the eigenvalues and eigenvectors, the relationship between those of a linear map and its adjoint. And obviously if we're talking eigenvalues and eigenvectors, then these are operators. T is an operator, its adjoint is an operator. And then we will look at the next corollary, which talks about if we have distinct eigenvalues, then that implies that we can actually have a basis of orthonormal eigenvectors. Before, when we spoke of distinct eigenvalues for a linear operator, that just gave us what? Linearly independent eigenvectors. Now, if our maps are normal, we can do even more. Now those eigenvectors are orthogonal, not just linearly independent. Then we will get into spectral theorems. It's actually easier to think about these over the two different fields. One being the complex field, and that's actually easier, or it has more immediate results in that if our map is normal and we're playing on a complex inner product space, then we immediately have an orthonormal basis of eigenvectors. If we go to the real inner product space, then we've learned that real sometimes has limitations. We can do a rotation and not even have an eigenvalue. So when we open up the field, or maybe restrict the field to be real, then we have more difficulty in terms of making these connections. And because of that, we need to introduce some background information before we jump from complex inner product spaces and normal and real inner product spaces. If we have real inner product spaces, then the operator needs to not just be normal, it needs to be self-adjoint, which is more restrictive, in order to have an orthonormal basis. The background that we will rely on, we're going back, somebody said, is the final exam comprehensive? Of course it's comprehensive. We have to remember all of this material, this great information that we have in previous chapters. Here's one example. We need to remember Cauchy-Schwarz, which shows us this relationship between the magnitude of an inner product and the norms of those vectors in the two slots of that inner product. We'll use that. We'll go all the way back to your elementary school days. So comprehensive. We are really comprehensive now. We need to remember how to complete the square. And what does that mean? That means now that we can apply that to this idea of having a positive operator. We can think of having a positive quantity, a positive real number. If we have a real number and we square it, that's positive. And so we want to complete the square and then generalize that. Remember we talked about these relationships or these connections of numbers and maps, meaning, if we view a linear map as a complex number, if we looked at the scalar case, then the adjoint of that map was, if the linear map is a complex number and we want the adjoint of that linear map, then that connection says, just conjugate that complex number. So that idea is helping us generalize from this elementary school notion of completing the square, so that we can use that completing the square and some other lemmas, which are lower forms of theorems, but we have lemma 726, which says that this quadratic looking linear map, t squared plus alpha t plus beta I, when that's invertible, what conditions exist between alpha and beta? And when t is self-adjoint, then it has an eigenvalue. We'll use that background information to then be able to conclude that if T, our linear operator, is self-adjoint, we can have an orthonormal basis. And that means that is diagonalizable when we have this orthogonal basis. But it's more restrictive, and we have to use this background information or keep things comprehensive. We have to make sure that we remember what we learned in the past. So now let's talk about normal operators. A normal operator on an inner product space, and right now I have not qualified that with a preceding adjective. It doesn't have to be complex or real. I'm just saying on an inner product space in general, it could be either, is one where the operator T commutes with its adjoint, or T applied to T adjoint is the same as T adjoint applied to T. And we know how to apply these linear maps to vectors. So this is saying you sort of cascade these operators with T, T, dagger, that's equal to T, dagger, T. That means that your map is normal. What are some observations that we can make? We'll make two. All self-adjoint operators are normal. So if you have a self-adjoint operator, and what do we mean by it being self-adjoint? What is a self-adjoint operator? Let's not forget, or a lot of this, a lot of words, a lot of discussion, maybe without a lot of thinking. So I'm trying to get you to hone back in on what do we mean by something being self-adjoint. That just means that T, the linear map, is equal to its adjoint. T equal to T dagger then allows us to rewrite T, T dagger as TT. Well, TT, now we can dagger either one of those. Let's dagger the first one, and we end up with T dagger T. So that if we have a self-adjoint map, then we are assured that it's normal, because T dagger is equal to T dagger T if our map is self-adjoint. We can't go the other direction. We could have normal operators that are not self-adjoint, and that's the second observation. So we can have normal operators, but normal operators can include non-self-adjoint operators. A map does not have to be self-adjoint to be normal. And here's an example. So now let's put this into something we can sort of maybe think about. Suppose that we look at the following matrix representation of a linear map T, and I'm assuming the standard basis, which is orthonormal. And what does that allow us to do? When I have an orthonormal basis and I'm talking about maps and their adjoints, what that allows is that I can now relate the two matrix representations of those operators. I know the matrix representation of the linear map here, but if I now want the matrix representation of its adjoint, how is it connected to this matrix A? As long as the bases are orthonormal, I can now do the complex conjugate transpose of this matrix to obtain the matrix representation of the adjoints map. Playing on being comprehensive, what's the linear map of T? If this is the matrix representation of T, can you now write down the linear map in terms of x and y? So now this first slot, or first component, is 2x minus 3y. So now this is piece of cake. This you can easily do. And this is now 3x plus 2y for the second component. We're okay with that. based on the matrix representation. Now, what's the matrix representation of T dagger? I already gave that away, didn't I? That's the conjugate transpose of A. And here we don't have any imaginary component, so it's just the transpose. And now we have 2, 3, minus 3, 2 for the matrix representation of T dagger. Is that okay? Now you know what I'm going to ask, right? What's the map associated with the adjoint of T? Well, now we can just fill that in based on what we just derived to be its matrix representation. This is now 2x plus 3y for the first coordinate, and minus 3x plus 2y for the second. And hopefully you can see that the matrix representations are not, or this is not a self-adjoint map based on these matrix representations. The matrix representations would have to be equal to the transpose, right? If it was self-adjoint, and that's not the case here. A is not equal to B. But what can we see if we know B? Now I'm going to have you memorize B and, well, I already wrote down A, so I don't need to worry about A. There's A, but B is now 2, 3, minus 3, 2. So that the product of those matrices, the combination of those, form a new map. So this you could think of as T dagger in terms of matrix representation. And what does that equal? Now I have 4 plus 9 in the 1, 1 entry of that product. Or I have 13. What's in the 2, 2 entry? I'm sorry, the 2, 2 entry, the other diagonal is 9 plus 4, isn't it? So the same number. Now, what about the 1, 2 entry? That's now 0. It's 6 minus 6. And the 2, 1 entry? 0. So there's the combination of the two maps in terms of their matrix representation. What about BA? You all have your BS, so you don't really think about BA. Sorry. Bachelor of Arts or something. You have a Bachelor of Science. I don't know where that came. Oh, BA, or B is 2, 3, minus 3, 2. I need to just concentrate, don't I, on what we're working through. And now what do we have for this product? The same as above. We now have 4 plus 9, or 13, in that space or location or that element. We likewise have 9 plus 4 in the 2, 2. And we have 6 minus 6 in the off diagonals. What am I trying to show or illustrate? Here is an example of a map that is normal, but it's not self-adjoint, because T dagger is equal to T dagger T, but T is not equal to T dagger. That's all I'm showing. So now let's return to this idea of T being normal, and that doesn't mean that we also have maps that are weird. This is normal in the scientific sense, not normal and weird. So now we have T is normal if and only if the norm of TV is equal to the norm of T dagger V for all V. That's the label on proposition or theorem 720. Here's the statement. If the operator T, or an operator T, that's what we mean by t as an element of L of v, is normal if and only if the norm of t, v, is equal to the norm of t dagger v. So let's show that or prove that. What's the proof? Well, we're starting with t being normal. And what does that mean? From before, t being normal said that t needed to be, or needed to commute with its adjoint. Or we could now say that t dagger is equal to t dagger t. But if that's the case, then I hope you can see, and now I'm going both ways, I'm saying if and only if, t dagger is equal to, or t dagger minus t dagger t is equal to 0. Just subtracting t dagger t from both sides based on the definition of normal. But now I can view that t dagger minus t dagger t as a linear operator, which is the 0 operator. And if that's the case, I can actually use it in an inner product. Since I have an inner product, suppose now that I say, oh, I'm going to apply t dagger. Actually, why did I change it up? Can I do it the other way around? For some reason, I'll get mixed up if I do it the other way. Can I do this? T dagger t minus t dagger. Is that okay? Same thing, I just have to subtract one from the other. So now I'm going to say that I have t dagger t minus t dagger. That's the 0 map applied to a vector v and v. And what does this end up being? That's now the 0 vector, isn't it? Here's the 0 vector. This is the 0 map. So that 0 is kind of used all over the place. But now we have the 0 map, and we have the 0 vector. And the 0 vector, you know, is orthogonal to every vector in V. So that now we can say this is equal to 0 for all vectors in our vector space. And now we can just play with all the properties of the inner product. We know that's a true statement based on what we know about inner products and the 0 vector being orthogonal to every vector in the space. And we created a 0 vector by applying this 0 map to the vector v. Not anything real major going on here. So now let's use the properties of inner products with this expression. So first let's do the additivity of the first slot. That now allows me to distribute that operator into two pieces. Or now I have, and I'm going to write it maybe a slightly different way, I'm going to group t with v and then apply t dagger. That's the first term, and then I subtract t applied to t dagger v applied to v, and that's still equal to 0. Are we okay with what I've done there? And that's true for all v. That's just additivity of the first slot. But I also can use now the definition of the adjoint to move that non-parenthetical operator into the second slot in both inner products. Meaning, if I now, ooh, I can't spell today, can I? Sorry. You can correct me. Had to run it through the spell check when I looked up there. Going back to that BS and BA, you're going to question whether I have either one of those. Okay, now let's go back to the definition of the adjoint. Luckily, those that are at home are not seeing the animation that is taking place in class with somebody up front. Let's now apply the definition of the adjoint. Meaning, let's take this first inner product and move that first operation, that T dagger, into the second slot. And what does that mean? Or what does that look like? I have to dagger it, right? So now I have TV, that's coming from this one. But now if I move that T dagger into the second slot, is that okay? And what else do I, now let me do the same thing with the second inner product. Now I move T into the second slot and I have T dagger V, and now I have T dagger V, and that is equal to 0 for all V. Are we okay with what I've done? And do you remember what we know T dagger dagger is? Take the adjoint of an adjoint. Oh, that goes back to an earlier lecture, doesn't it? Where we were getting rid of the AD and the AD. Never mind. Here's T, okay? We were, oh gosh. So that what do I have? Now I have, rewriting that, this just isn't the same live versus recorded, is it? Oh well. TV inner product with TV minus T dagger V inner product with T dagger V, and that's equal to 0. And I'm going to quit writing for all V except at the end. What do those two inner products equal? The norm squared, right? So this now says that I have TV, the norm of that squared, minus the norm of T dagger V squared, equaling 0 for all V in V, and I'm saying that we can close that up with a square. So there's our justification that if we have a normal operator, then the norm of TV equals the norm of T dagger V for all V. We looked at one of those operators, so let's now just make an observation, or in the process of working through that proof, the operator T dagger T minus T dagger is self-adjoint. And if T is normal, that's the 0 map, but if T is not normal, it's a map of something. But whatever that map is, it's self-adjoint. And we can show that by simply remembering or applying some of our knowledge of adjoints. Or we're trying to show that if we have T dagger T minus T dagger, and we take the adjoint of that, it better be equal to what's inside the parenthesis. So that now, if I apply that, I have T dagger T daggered minus T dagger daggered. This is just trying to remember how to dagger things, right? And what happens when we dagger a combination of maps. And it's similar to what happens when we transpose matrices. Their order switches. So that now if I have T dagger T daggered, now I take the rightmost map, T, and dagger that and operate on T dagger dagger. That's our favorite, isn't it? T dagger dagger. Hopefully it's not too much of your favorite, but there we go. Okay? And what do we have for the other one? Now we have T dagger dagger times T dagger. And those adjoints of adjoints are T's, so that now we have T dagger T minus T dagger, and I sure hope that's what we started with, and it is. So that particular operator is self-adjoint. Whether it's the zero map or not depends on what? If T is normal, then it's the zero map. That really pushes things to nowhere, doesn't it? To the zero vector. All right, so now let's look at properties of T being normal. First, let's look at or examine eigenvalues and eigenvectors of both T and T dagger. And we'll also look at a second property, which is when we have distinct eigenvalues of T. And here we're assuming that T is normal. That was the title, properties of T being normal. So we're assuming that T is normal, and now if we have distinct eigenvalues, then that will imply that we have orthogonal eigenvectors. Again, what happens if we don't have T being normal? If T is a linear operator and we have distinct lambdas, what do we know about the eigenvectors? They're linearly independent. They're not orthogonal, but they're linearly independent, which is a start. That's something. All right, so now let's look at, well, before we even start doing that, prior to stating and proving, what is Corollary 721, let's verify a lemma. And this lemma is actually as follows. If T is normal, then the following map, T minus lambda I, is also normal. So if you have a linear operator that's normal, then T minus lambda I is likewise normal. Let's prove that lemma. So now what we want to do is actually show that T commutes with it, T minus lambda I commutes with its adjoint. That will show that it's normal. So we're now trying to show that T minus lambda I operating on T minus lambda I adjoint is the same as t minus lambda I adjoint operating on t minus lambda I. And the wording of that is really that t minus lambda I, if you just wanted to state this, if you went home tonight and started talking to your buddies or roommates or mom and dad, you just might say, yeah, t minus lambda I commutes with its adjoint. I'm sure that would start a very interesting discussion, maybe more so than the election tomorrow. Just saying. So now t minus lambda I commutes with its adjoint. That's the wording of what I just showed above. And what we are actually using are two results. What is the adjoint of a complex number? If lambda is a complex number, what happens when I ask for its adjoint? It's its complex conjugate, isn't it? So this is now lambda star. So in any of this, when you see a dagger applied to lambda, we can replace that with its complex conjugate. Likewise, what happens if I dagger the identity map? That gets us back, or that just leaves us with the identity map. And you can show this through the inner product if you want to convince yourself that lambda dagger is equal to lambda conjugate. It's basically pushing things between slots in the inner product, and you know what happens to homogeneity of the first slot and what happens in the second slot relative to homogeneity. Conjugate homogeneity, isn't it? So there's where that comes from, and when we switch something from first to second slot, that's similar to taking its adjoint. All right, so now let's look at this sort of in two pieces. Let's look at the left-hand side and push all of those operations through, products and adjoints, and then we'll look at the right-hand side, and then hopefully we'll see that all of that algebra gives us the same formula or the same expression. So here, let's start with the left-hand side of this map and its adjoint. So now I have t minus lambda I times or operating on its adjoint. That's the left-hand side. I now have t minus lambda I operating on t minus lambda I adjoint. And using what I just said up above, what happens when I push that adjoint through or inside that right-hand expression? I have t dagger minus the conjugate times I. Is that okay? So now I can multiply that out. I now have t times t dagger, and which way did I want to do it? Minus, let's say, lambda I t dagger. So now I'm distributing the first through on the individual pieces on the right, minus lambda, well, let me just preserve the order, t lambda star I plus lambda lambda star I. And the lambda is a scalar, so this now says that I have t dagger minus lambda t dagger. I can collapse the identity map. I can pull the lambda conjugate out front and forget about the identity map in the third term. And what happens when I take a complex number and multiply it by its conjugate? Now it's just the magnitude squared. So now I have the magnitude of lambda squared times I. That's as much as we need to reduce the left-hand side. Hopefully when we push all of this through on the right-hand side, we end up with those same terms. So now the right-hand side, we started with t minus lambda I dagger times t minus lambda I. And again, applying the dagger to lambda and I allows us to say we have t dagger minus lambda star I operating on t minus lambda I. Or if we push those through, I now have t dagger t minus lambda star I t minus t dagger t, whoops, did that already, t dagger lambda I minus lambda star lambda I. And that was a minus, so I have a plus, right? And what do I know about t? What was my assumption in this lemma? If t is normal, then t minus lambda I is also normal. So if I need to, I can use the fact that t is normal. And I'm going to use that now to change t dagger t into something that looks like the blue up above. Since it's normal, I can do that. It commutes. So now I know that t dagger t is the same as t dagger. And here I simply used t is normal. And then I have a minus lambda star t. I have a minus lambda t dagger plus lambda magnitude squared I. And hopefully you can kind of see that we do have all four terms in both final expressions for the left-hand side and the right-hand side. So that's now the proof that if I start out with with an operator that's normal, then I can conclude immediately that t minus lambda I is normal. And that's going to be helpful in this next corollary, in showing it. So here's corollary 721. Corollary 721 says we're given a linear operator, t, that is normal. So that's what we're starting with. And now, if v is a vector in our vector space capital V, is, in fact, it's more than just that. Let's say that it is an eigenvector. Of t with eigenvalue let's just say it's lambda in our field F, then that same vector V is also an eigenvector of the adjoint of t with eigenvalue equaling the conjugate of the original eigenvalue lambda. So now, given that t is normal and t has v as an eigenvector and lambda as an eigenvalue, then if you need the eigenvalues and eigenvectors of its adjoint, you just conjugate the eigenvalues, and the corresponding eigenvectors with lambda are associated with lambda star in its adjoint. So here's the proof of that. Take V and lambda as an eigenvalue eigenvector pair of T. That's given. That means then that we have something that you probably have ingrained, and hopefully you won't even forget this until you retire, right? The eigenvalue eigenvector relationship. TV is equal to lambda V. Or you could rewrite that by subtracting lambda V from both sides and factoring out the vector V using the identity map I to say that T minus lambda I V is equal to 0. So now, from the above lemma, T minus lambda I is normal, since T was normal in this corollary. And if T minus lambda I is normal, then from proposition 720, we now know that T minus lambda I V is equal to what? The adjoint of that operator, T minus lambda I, applied to the same vector V, but we know that T minus lambda I V is the 0 vector, so the norm of the 0 vector is 0 for both cases. And what can we do here? Well, here we could push that dagger through. If we wanted to see it a little bit more clearly, we could say, oh, this is T dagger minus, what's the dagger of lambda? The conjugate. And there it explicitly shows us that this is an eigenvalue eigenvector problem for T dagger and lambda star. So that now, therefore, V, the same vector, is an eigenvector of T dagger. And with respect to that eigenvector, we have an eigenvalue being equal to its conjugate. So now if somebody tells you that they have an eigenvalue eigenvector pair of an operator, T, you now know, and if T is what? If it's normal, now you know what its eigenvalues and eigenvectors are equal to. And that requires that T is normal. And being normal says that T and its adjoint commute. So we're looking at more specific or more particular kinds of operators. So now let's look at another corollary. Corollary 22. Suppose we're now given that T is a linear operator and it's normal. The eigenvectors of T corresponding to distinct eigenvalues are orthogonal. And now this is a more powerful result than we've had up to this point. We had t being an operator, and if we had distinct eigenvalues of that t, then that gave us linearly independent eigenvectors. Now we're saying more. We're saying that if you give me a normal t, then the eigenvectors of that operator associated with distinct eigenvalues will be orthogonal. Now we can put them in an inner product and find that they have an inner product of 0. So now let's look at the proof of that, or show that. So now let's take alpha and beta as distinct. Don't ask me why I've now changed to alpha and beta instead of lambda 1 and lambda 2, but so be it. So now I have alpha and beta as distinct eigenvalues of this normal operator t with eigenvectors and now let me call those u and v respectively. I guess I got tired of subscripts. So now I have alphas, betas, u, and v. That now says that I have, if I apply t to u, that's going to give me alpha u, and if I apply t to v, that's going to give me beta v. That's the eigenvalue-eigenvector relationship for alpha u and beta v. Now let me just form a new expression or equation. Suppose I take alpha minus beta, and that's a scalar, and I apply it to the inner product of u and v. What am I hoping? I'm hoping that I can show that that inner product of u with v is what? If I want u and v to be orthogonal, I need that inner product to be 0. So now let me just start with this expression and see if I can conclude that that inner product is 0. Suppose I now push that alpha and beta, or just basically separate this into two expressions. I can now say that that's alpha times the inner product of u and v minus beta, times the inner product of u and v. Haven't done anything magical yet. But now let me push that through. Let me move alpha into the first slot. That's easy because there's homogeneity of the first slot. That now says that I have alpha u comma v. But let me push beta into the second slot. And if I push beta into the second slot, I now need to conjugate beta. So now the conjugate of beta is applied to v. But what do I know alpha u equals? That's just tu, right, by the eigenvalue-eigenvector relationship. So now in the first slot, I actually have tu inner product with v. And what do I know about beta star in the second slot? Now that's associated with t dagger because what? T was normal. So now I'm using the fact that t was normal. I think I said that was Corollary 721, that t is normal. So that now I have u inner product with t dagger v. Because I knew that beta was an eigenvalue of t, and v was its eigenvector. And t dagger has beta star as its eigenvalue and v as its eigenvector. But what is this? Can I rewrite that? Can I use the definition of the adjoint to slide that T dagger into the first slot? And now that allows me to say, oh, that's TU inner product with V. So that now I have the inner product of TU with V, and I take away from that the inner product of TU of V. This was just the definition of the adjoint. And using T being normal, that allowed me to change beta star V into T dagger V. That's now equal to 0. Or what have I now concluded? Now I know, so I've now, whatever I started with, which was this alpha minus beta times, that's scalar, times this inner product u with v, now I've shown that that expression is 0. But what do I know about alpha and beta? They were distinct, weren't they? That's what I was assuming, and now their difference is obviously going to be something other than 0, so I know that alpha minus beta is not equal to 0, and the product of that with this other scalar, which is the inner product of u and v, is 0, so that forces the inner product of u with v to be 0. Or, since alpha and beta are distinct, alpha minus beta is not equal to 0, so I can divide through by that if I wanted to, or said another way, I can now conclude that the inner product of u and v, which were two eigenvectors of the operator t, are now orthogonal. So this is now the definition of vectors being orthogonal. And we can put a box at the end of that. What are we doing? Well, we're trying to end up with specifying some of these operators to make them look special or nice. So now we're ready to state the spectral theorem. And before we state that, let me just write. So now I need to get my hand all loosened up because I'm going to do quite a bit of writing. So here, let me just try to write. We now come to the end of our quest to find nice bases for this vector space so that we could now diagonalize or get matrices that are as close to diagonal as possible. And now I've already basically said what I am trying to write now. Remember the appeal of diagonal matrix representations. It's pretty easy to see what's going on or to understand what this big vector space is doing when you have a diagonal matrix. Now you can kind of isolate it to one-dimensional things instead of n-dimensional. Remember also that an operator only has a diagonal representation if there exists a basis consisting of eigenvectors of the operator. We'll add further constraint, we'll add a further constraint that we'd like orthonormal basis. We'll add a further constraint that we'd like an orthonormal basis. And if we're dealing with orthonormal or magnitudes of vectors, then we have some inner product going on. So we must be in an inner product space. The spectral theorem tells us which operators have eigenvectors that can produce such an orthonormal basis. And therefore, which operators have a nice diagonal representation. Now, as I said leading in or beginning this time together, it actually depends, our answer depends on which field we're playing in, whether we're playing in the complex field or the real field, or the answer depends on whether we are dealing with a real or complex inner product space. And because of that, we'll look at both separately. So we'll treat the two cases separately. Okay, now let's state the complex spectral theorem. And that's theorem 24 in chapter 7. Complex spectral theorem. Suppose that our field is now the complex field of numbers, and T is a linear operator on that vector space. Then the following statements are equivalent. A, if you give me, or if you can determine that T is normal, then we can say the other things automatically. T being normal is equivalent to saying that V, the vector space, has an orthonormal basis consisting of eigenvectors of the normal operator. So if T is normal, now we can find the eigenvectors of T, and we can actually make those eigenvectors orthonormal vectors, and they will form a basis for this vector space. C, T has a diagonal matrix with respect to some orthonormal basis of T. So now let's see, and what's our strategy if we're now saying that these three statements are equivalent? Okay, they all imply each other, right? But now, can we say anything about B and C based on our comprehensive knowledge of this material? If I give you T, there is a theorem or a proposition, isn't there? Remember exam number 2, studying for that? So now the proof, we've now simplified a little bit because we can actually say that B and C are equivalent if we go back to, follows from proposition or theorem 41 in chapter 5. Which is dealing with what? Linearly independent eigenvectors. Then we can diagonalize this. Now we just have a basis. We have it a little bit more specified. Now it's orthonormal because we can make them that, but 541 tells us we have a basis of eigenvectors, then we can diagonalize that linear map. So this is now B and C are equivalent conditions for diagonalizability. So now let's just show that C implies A, and then A implies C, or whatever. So now we'll start, or we will first prove that if we start with C, statement C, that actually implies statement A, that T is normal. So if we can diagonalize what was C, T has a diagonal matrix with respect to some orthonormal basis of T. So now we can just say we have a basis, an orthonormal basis, that allows us to diagonalize the matrix T. And now we can basically try to show that that t is normal. So now let's do that. Here is C implying A. Or we can now assume that V has an orthonormal and this orthonormal means that we're dealing with an inner product space. We have some way of measuring magnitude of these vectors. Assume V has an orthonormal basis of eigenvectors of this linear operator T. That means from proposition 521 that T has a diagonal matrix representation with respect to this basis. And if this is an orthonormal basis, what does that also allow us to conclude about if I now had the matrix representation of T, how do I know that is related or connected with the matrix representation of T dagger if I have an orthonormal basis? That's when we can do the complex conjugate transpose of these matrix representations. So this is now saying that if we need the matrix representation of the adjoint, since we're working on an orthonormal basis, then we can take the conjugate transpose of the matrix representation of T. So we're using all of this, or it's built in with this information. So now the matrix representation of T dagger is the conjugate transpose of the matrix representation of T. Therefore, T dagger, what does it look like if we know what T is? T has a diagonal matrix representation. What does T dagger have? If it's the conjugate transpose of what structure does the matrix representation of T dagger have if the matrix representation of T can be diagonal? It's also diagonal. So now, therefore, T dagger also has a diagonal representation with respect to this basis. Now let's just sort of put this into some more concrete understanding by just looking at the product of two diagonal matrices. Consider the product of two diagonal matrices. Suppose that I now have A1, A2, AN, and I have B1, B2. these are associated with operators, so they're square and they're the same size. A, let's say, corresponds to t, and B corresponds to t dagger. What happens to the product of this? If I multiply this diagonal A with this diagonal B, what do I end up with? I get the product of the diagonals. I have A1, B1, A2, B2, etc. A sub n, B sub n. And what happens if I do just the opposite? What if I take B and multiply by A? Same. So now these matrix representations commute, do they not? So what does that say about T and T dagger? Or they commute, so they're normal. So now we've shown that C implies A. And maybe what I will do offline, wow, is show that A implies C, and maybe that will be it. So that will be a few pages, but I'll fill in the gaps, and you can see those after class notes, but that's what I'm suggesting we can do. Hopefully you now can believe that C implies A, that having this diagonalizable orthonormal basis for the map implies that T is normal. Then we'll go the other direction and we'll call it good.